Imagine for a second that you drop a single grain of white sea salt onto like a really thick, bright white shag carpet.
Oh, wow, that sounds impossible.
Right. Now get down on your hands and knees and try to actually find it. That right there, that is the exact visual challenge doctors are facing every single day when they look for the earliest, microscopic signs of breast cancer.
Yeah.
You're searching for something that's incredibly tiny, and it's completely hidden within this chaotic, heavily textured background that is literally the exact same color.
And, I mean, the stakes of that specific visual search are just astronomical. Missing that one tiny speck could literally mean the difference between catching a malignancy at its absolute most treatable stage or, letting it silently develop for a whole other year before it actually forms into a palpable mass.
Which is terrifying.
It is. And to help doctors out, the medical field has spent years, decades really, trying to train artificial intelligence to scan these images and flag those tiny specks automatically.
Which honestly sounds like a perfect job for an AI, right?
You'd think so, yeah.
But the traditional way we've been teaching these models is by handing them millions of examples where human experts have painstakingly circled every single grain of salt, literally pixel by pixel.
Which is incredibly tedious.
Yeah, it's a massive human bottleneck. And bypassing that bottleneck entirely, well, that is the mission of today's deep dive. We are exploring a cutting-edge research paper that was submitted in April 2026 titled MC-GenRef.
A really fascinating paper.
It really is. The researchers have essentially figured out how to train an AI to find these microscopic cancer indicators without ever using a single human-drawn label.
Okay, let's unpack this. Before we really get into how the AI pulls this off, we need to understand the physical reality of what we are actually looking at on these scans.
Right, so the clinical term for those specks is microcalcifications, or just MCs. Basically, these are microscopic calcium deposits inside the breast tissue, and calcium absorbs X-rays very efficiently, so on a typical mammogram, they show up as these tiny, bright white specks.
Are they always a sign of cancer, though? No, not at all. Not all calcium deposits are dangerous. Some are honestly just benign byproducts of aging. But when you see specific formations, like what we call scattered puncta, or tightly clefted patterns of very fine specks, that is often the very first radiographic footprint of an early-stage malignancy, things like ductal carcinoma in situ.
Wait, if these specks are literally microscopic, how does a doctor even see them on a standard scan? I'm picturing, like, a massive, super high-resolution medical monitor. Are they just hunting for a single bright pixel?
Sometimes, yeah. Sometimes they're literally looking for something that is only 2 or 3 pixels wide across an image that contains millions of pixels. The paper actually describes finding them as an adversarial vision problem.
Adversarial, like the image is fighting back.
Exactly, because the breast is mostly composed of glandular tissue, fat, and ligaments, right? And on an X-ray, glandular tissue is incredibly dense. It creates this chaotic, high-frequency overlapping texture. So getting back to your opening imagery, the glandular tissue is that bright white shag carpet.
Oh, I see. So a weirdly twisted carpet fiber, or like a dense knot in the rug, could easily throw a shadow that tricks your eye into thinking you found the salt.
Exactly. And then you have to add the natural physical noise of the X-ray machine itself on top of that.
Like static.
Yeah, pretty much. When the X-ray photons hit the digital sensor panel, there's always a slight scatter, like a tiny bit of electronic static embedded in the image. That acquisition noise acts like a camouflage net thrown over the entire thing. And this completely breaks traditional deep learning models.
Why is that?
Well, normally, you train an AI using dense pixel-level labels. So you set a highly trained radiologist in a dark room, and they zoom in 400% on a monitor, right? And they try to draw a digital boundary around the exact border of that tiny calcium speck.
But if the speck is only 3 pixels wide and it's covered in static, how does the radiologist even know where the calcium ends and the healthy tissue begins?
That's the thing, they don't. The boundary becomes incredibly subjective.
Yeah.
One radiologist will draw a circle encompassing, say, 5 pixels. Another doctor, looking at the exact same image, might only circle 2 pixels. The underlying ground truth is just inherently fuzzy, and the appearance of the tissue also changes depending on whether the hospital uses a machine manufactured by one vendor versus another.
Oh, so the machines themselves look different.
Exactly. The X-ray tubes are different, the sensors are different. Trying to create a massive data set with perfectly agreed-upon human labels is practically impossible. This raises an important question. How do you train a highly sensitive AI to find a critical target if the human answer key you are forcing it to study is inherently flawed, contradictory, and overwhelmingly expensive to generate?
And the researchers behind this 2026 paper answered that by simply throwing away the human answer key?
They really did.
They just stopped asking doctors to circle the dots. Instead, they decided to fake it. They built a system utilizing what they call synthetic supervision. If humans can't provide millions of perfect examples, well, the researchers just used math to build the examples themselves.
Now, I should clarify. The concept of synthetic data isn't entirely new, but models trained on entirely fake data usually crash and burn in the real world.
Because reality is messy.
Yeah, and neural networks are famously lazy.
Yeah.
They will always look for the absolute easiest mathematical shortcut to solve a problem. So if you just take a black image and drop perfectly round, bright white digital circles onto it, The AI doesn't learn what a complex biological calcification looks like.
Right, it just learns what a fake circle looks like.
Exactly. Just learns to spot the sharp edge of a digitally drawn shape.
Which means the second you show it a real, messy mammogram full of organic shapes and static, the AI is going to fail completely. So how do they avoid that trap here?
By anchoring the synthetic data in organic reality, they don't generate the entire breast scan from scratch. They actually pull real, healthy negative patches from the RSNA screening dataset.
Wait, what's the RSNA dataset?
It's this massive database of actual patient mammograms that have been definitively cleared of cancer.
Ah, okay. So they are using real, healthy white shag carpets as their background canvas.
To preserve the chaotic texture of actual human biology, yes. And then they mathematically generate the microcalcification patterns and inject them into those real backgrounds. But the injection process is where the true high-fidelity physics come into play.
So they aren't just photoshopping white dots onto the scan.
No. They are actively simulating the physics of a mammography machine.
Okay, walk me through that physics simulation. How do you mathematically guarantee that a fake dot actually looks like it was captured by a real X-ray machine?
Well, you have to emulate the optical degradation of the scanner. When an X-ray beam passes through a dense object, like a tiny calcium deposit, the edges aren't perfectly sharp on the final image. They blur.
Like an out-of-focus camera.
Exactly. So the researchers apply mathematical functions called blur kernels to their synthetic dots to mimic this specific optical blur. They also analyze the mathematical statistics of the surrounding real breast tissue, like how dark or light the immediate pixels are, and they adjust the local contrast of the injected dot, so it blends seamlessly into that specific neighborhood of the image. They're mathematically modeling the exact physical scale, the irregular morphology, and the clustering geometry of actual malignancies.
And because they wrote the mathematical formula to generate the dot, they know the absolute pixel-perfect boundary of that shape. So they have a flawless answer key for the AI to study.
Zero human subjectivity, zero labeling cost, and millions of physically plausible training examples. The AI learns the foundational shape, size, and clustering behavior of these anomalies by studying these hyper-realistic simulations. It establishes a morphological anchor, essentially mastering the concept of what a calcification looks like when it's buried in glandular tissue.
But I mean, even with the most advanced blur kernels and physics simulations in the world, a simulation is still just a simulation, right? There's always going to be a domain gap between the lab and the chaotic reality of a living patient. Here's where it gets really interesting.
Yeah, this is my favorite part.
The researchers didn't just teach the AI the rules of the road using simulations and then just hope for the best. They gave the AI a tool to actively adapt when it faces a real patient scan. They developed test-time generative posterior refinement, or TT-GPR.
Right, and to understand why that's huge, you have to look at the traditional paradigm in medical AI, which is the single forward pass. An AI looks at a scan, runs a single massive calculation through its neural network, and spits out its final decision.
Just one look.
Yeah, it looks once, guesses once, and moves on. And that approach is incredibly fragile when you're dealing with microscopic targets that are heavily camouflaged by noise.
I mean, a one-and-done guess feels wildly irresponsible when a patient's life is literally on the line and the target is just a few blurry pixels.
Absolutely, and the TT-GPR framework completely dismantles that one-and-done approach. It treats the visual search as a process of approximate posterior inference.
Which means what, exactly?
Instead of just guessing, the AI is programmed to actively question and refine its own initial assumptions in real time while it is looking at the new scan. The architecture utilizes two distinct systems working in tandem to achieve this.
Okay, let's break down those two systems step by step. What happens the exact moment a brand new, unseen patient scan is fed into the machine?
So the first system is the base segmentor. You can kind of think of this as the scout. It scans the messy, complex, real-world mammogram and makes a rapid, tentative guess based on what it learned from the synthetic training data. It flags areas that look suspicious.
Okay.
The researchers refer to this initial rough map as a sparse seed. It's essentially a grid of coordinates saying, I think there might be something at these locations.
So the scout drops a few pins on a map. What does the second system do?
The second system is a rectified flow generator. Flow models are these incredible mathematical tools. Their entire purpose is to understand the fundamental idealized structure of an object, stripping away all the noise and chaos.
So it cleans it up.
Exactly. This generator takes that rough, sparse seed provided by the scout and hallucinates a pristine, mathematically perfect image of what those calcifications should look like, entirely devoid of the X-ray static and the overlapping glandular tissue.
Okay, I want to make sure I'm visualizing this clearly. Let's say, imagine I am a detective trying to sketch a suspect's face, but I'm standing in a dark, heavily fogged alleyway.
Right, the foggy alleyway is the noisy mammogram.
Yes. So I peer into the fog, make out a few rough shapes, and I quickly sketch a tentative outline in my notebook. That is our base segmentor creating the sparse seed.
Spun on. Then you hand that rough outline to a master forensic artist sitting in a brightly lit, sterile studio. The artist takes your hasty lines and draws a flawless, anatomically perfect human face.
Yeah.
That is your rectified flow generator, creating the idealized surrogate target.
Got it. And then I take the artist's pristine sketch back into the alleyway, I hold it up, and I look back and forth between the perfect drawing and the actual fog.
Checking the work.
Right. And I realize, oh, the sharp jawline the artist drew, based on my notes, is actually just the shadow of a dumpster. So I iteratively erase and update my own sketch, checking my work against the real world until I'm absolutely certain I'm looking at the suspect and not just a trick of the light.
That is exactly it. The AI is running that exact comparative loop mathematically. During test time, which just means the actual moment the AI is analyzing the patient, and the idealized surrogate target generated.
So it's looking for differences.
Yeah, it uses the actual messy edges present in the patient's scan to anchor its final decision. If the scout flagged a tiny bright spot, but during refinement, the system realizes that spot doesn't align with any solid physical structure in the actual image, it dismisses it.
It catches its own mistakes.
Yes. It systematically kills off pepper noise false positives. It is literally teaching itself how to see the specific unique texture of that individual patient's breast tissue on the fly.
Teaching a machine to second-guess its own observations is just a massive leap forward. So this detective sketching system sounds foolproof in theory, but, you know, hospitals aren't theory. When they actually tested this out on real patient scans, specifically the 𝗖𝗄𝗏 dataset, did the AI get confused by real-world fog? Let's look at the metrics, because an elegant theory doesn't cure cancer.
No, it doesn't.
Yeah.
And the 𝗖𝗄𝗏 dataset is a highly respected public benchmark in medical imaging, so it's a great test. The researchers first tested the baseline system without turning on the test time refinement, just the synthetic training.
Okay, so just the scout alone.
Right. And it achieved a DICE overlap score of 0.80. Now, the DICE score measures geometric precision. It calculates how perfectly the pixels the AI predicted overlap with the exact pixels the disease actually occupies.
Oh, wow.
Yeah. Hitting 0.80 with a model that has literally never seen a single human-drawn label is a staggering achievement.
But then they activated the TT-GPR. The detectives started looking back and forth in the alleyway?
Exactly.
Yeah.
But when the refinement process was activated, the DICE score actually dropped. It went down from 0.80 to 0.72. However, the recall, which measures the model's clinical sensitivity, its ability to actually find the hidden disease, jumped up to 0.89. Most importantly, the false negative rate plummeted down to just 0.11 or 11%.
Wait, but a drop in the pixel-perfect overlap sounds like the AI got worse. I mean, if you were presenting these metrics to a hospital board, a drop in a primary score like DICE usually means the algorithm is degrading, right?
Well, if we connect this to the bigger picture, you have to look at the real-world consequences of the errors being made. In cancer screening, not all errors are created equal.
That makes sense.
Right. If the AI draws a boundary that is 2 pixels wider than the actual calcium deposit, the DICE score goes down because the overlap isn't mathematically perfect. But clinically, the doctor still sees the flag, investigates the area, and finds the calcium. The patient gets treatment.
But a false negative means the AI completely missed the tiny speck. The patient is sent home, told they are healthy, and the malignancy continues to grow for another whole year. That is a catastrophic failure.
Exactly. And the AI architecture actually internalizes this clinical reality mathematically through something called Tversky loss weighting.
Tversky loss.
Yeah, you can think of the loss function as the AI's internal penalty system. In a lot of standard models, the penalty for guessing a picture is cancer when it isn't is the exact same as the penalty for missing a cancerous pixel.
Oh, that doesn't seem right.
It isn't. The Tversky loss acts like a built-in panic button. The math is explicitly rigged, so the algorithm feels severely mathematically punished for missing a real cancer speck, far more heavily than it is punished for accidentally flagging a slightly larger boundary around a healthy area.
Oh, I love that. It is actively trading a few points of geometric perfection in order to cast a wider, safer safety net. It's optimizing for human survival, not for just getting a high score on a pixel matching spreadsheet.
Absolutely. The in-breast data prove the system is incredibly sensitive. But in-breast is a known quantity in research circles. The ultimate test of any medical imaging AI is cross-site domain shift.
Cross-site domain shift.
Right. That's when you take the algorithm out of the lab where it was developed and deploy it on an entirely different hospital's computer system. The researchers use the external Yonsei cohort for this.
Okay, so these are scans from Severance Hospital at Yonsei University. We were talking about different patient demographics, completely different brands of X-ray machines, and totally different acquisition settings.
And cross-site domain shift is notoriously where deep learning models fail spectacularly. An AI often memorizes the specific invisible sensor noise pattern of the machines it was trained on.
Oh, like a watermark.
Exactly. It uses that watermark as a crutch. The moment you show it a scan from a new machine with a different invisible noise pattern, the algorithm just panics. It doesn't know how to process the new visual environment.
How badly did the older traditional AI models fail when they looked at the Yonsei scans?
The performance degradation was severe. Let's look at a previous method called 𝗤𝗏 FPN. When faced with the new hospital data, it tried to keep its sensitivity high, but it entirely lost its precision. Instead of pinpointing microscopic dots, it just started throwing massive, coarse boundaries over huge chunks of the breast tissue.
Yikes.
Yeah, it was basically throwing its hands up and saying, there might be something dangerous somewhere in this massive general vicinity, which is clinically useless.
A doctor can't biopsy a massive general vicinity based on a panicked algorithm's guess. So how did our synthetic self-refining model perform under that exact same cross-site pressure?
The test time refinement proved its value completely, because the TT-GPR framework forces the AI to actively calculate the gradient differences based on the specific image currently in front of it. It adapted to the new hospital's unique X-ray noise on the fly.
So it didn't need the watermark.
It didn't rely on memorized watermarks at all. On the 𝗖𝗍 cohort, activating the refinement increased the F2 score, which is a metric heavily weighted toward finding true positive cases, to 0.33.
Nice.
It actively sharpened its detections, effectively isolating the true clustered puncta while suppressing the strange new noise artifacts generated by the 𝗖𝗍 X-ray machines. It maintained its precision across entirely new environments.
So what does this all mean? When we look at everything we've explored today, the direct application for you, the listener, is that artificial intelligence is finally breaking free from the human bottleneck.
Right.
For the longest time, AI was just a mirror. We drew a circle on an image, and it learned to draw that exact same circle. Its intelligence was entirely capped by human fatigue, human subjectivity, and just the sheer financial cost of paying experts to build datasets. With MC-GenRef, we are seeing a system that learns the deep underlying physics of a disease entirely through simulated math, and then utilizes real-time generation to refine its own vision in the messy real world.
What's fascinating here is the mechanics of this breakthrough have nothing fundamentally to do with breast tissue or cancer.
Wait, really?
Yeah, the framework of injecting mathematically perfect synthetic anomalies into noisy, complex, real-world backgrounds, and then utilizing generative test time refinement to uncover them, that is a universally applicable approach to signal detection.
Oh, I see where you're going with this.
Think about astrophysics. Observatories capture petabytes of incredibly noisy telescope data, searching the dark expanse for the microscopic pixel-wide dip in a star's light curve that betrays the existence of an undiscovered exoplanet.
Right.
Or consider particle physics, where researchers sift through the chaotic, high-energy collision data at the Large Hadron Collider, looking for the momentary signature of a new subatomic particle.
And usually we just wait for humans to find it first to teach the AI.
Exactly. Instead of waiting years for human scientists to manually spot, verify, and label these anomalies just to teach an algorithm what to look for, we could simply inject simulated quantum particles or simulated planetary transits into the raw, ambient background noise of the universe. We teach the machine the pure physics of the target synthetically. Then, we unleash it on the raw data, allowing it to iteratively refine its own vision until the invisible suddenly becomes undeniable. If we can teach a machine to find the earliest signs of cancer hidden within the chaotic density of human tissue entirely without a human guide, what else in the universe is waiting to be found once we teach machines how to truly look for themselves?